Hey, good afternoon. It's 12:30, so it's time for us to start our lecture. And the first announcement for you guys this afternoon is that we have our first exam scheduled for Monday next week. So a week from today, we're going to have our first exam. And the material that's going to be included is up to what we're going to cover this afternoon. Okay, so everything from the beginning of the semester onto the material that we're going to cover today is going to be part of the material for the first exam. On Wednesday, we're going to have a review. So typically what I do in the review is I discuss the format for the exam and the type of questions that you should expect, and then go over the material that was covered during that period of the course. And then also give you an opportunity for asking questions. So if you have questions about any problems that you have worked on, or in general about the material, on Wednesday is a good opportunity for you to bring those, and we can discuss those in class. So again, our first exam is going to be on the next Monday, and the 21st, I believe. And it's going to be during the class period. So if you are, you have to be available during this class time period. I haven't decided yet if you're going to do an online exam or in-class exam. I'll be deciding that tomorrow. But I will talk more about the format of the exam on Wednesday. If the exam is in class, then everybody has to be here in order to take the exam. I haven't found a larger classroom yet, so we will be here. And you have an hour and 20 minutes to work on the exam. But we'll talk more about that on Wednesday. Today we're gonna continue our discussion on layout models, planning models, and design algorithms. So our previous lecture, we discussed different alternatives that you have to build. These are construction type of algorithms in which you're gonna have information about the type of departments, have information about the flow between these departments, and then using that information, costs associated based on the distance, you decide, or the algorithms show you how the layout or configuration for the departments inside the facility should look like. So I believe your homework, your assignment, your current assignment had some problems about that. Today we're gonna continue that discussion. We're gonna talk about other design algorithms. These are more improved type of algorithms in which you begin with something. You begin with a layout, and then you're trying to improve that layout based on the current information. So let's get started. Any questions? So as always, we start our lectures with this. We've been looking at the formulation models and analytical procedures for the study of facilities layout planning as part of this lecture. And the agenda is a continuation of what we did already. So introduction to basic layout types, layout procedures, and then algorithm approaches. And in terms of the learning objectives, again, we are gonna understand the interactions between layout planning models and design algorithms as they relate to facilities planning. So I think I show you this information already. There are layout procedures presented in the previous section provide a framework to construct or improve a layout, but they don't provide a formal procedure or algorithm for some of the critical steps associated with the design of an evaluation. So the models and algorithm we present in these sections provide us with objective criteria to facilitate the evaluation of various alternatives that emerge in the process. So now we're going to have this objective function that is going to be updated every time that we change or we perform an iteration in the algorithm. So if we switch to departments, we're going to compute a new performance measure. We're going to see whether or not that performance measure is better than what we had before. So we have two ways to measure, right? We had two types of objective functions. I don't know if you remember. One was trying to minimize the overall distance. And then also we're looking at minimizing the multiplication of the cost, distance, and flow. So those are two objective functions that we are working with. And then we have different type of information that we can use as part of our decision process. So most layout algorithms can be classified according to the type of input data that requires. So we have qualitative flow data, quantitative flow data, and some algorithms will combine the use of both. So here are the two objective functions that I was mentioning. So algorithms can be classified according to the objective functions. So minimizing the sum of the flow times distances, and then maximizing the adjacency score. So we want to put together those departments that have more interaction. So if we are solving the problem by looking at maximizing an adjacency score, we might not be getting the same solution as when we solve looking at the minimization of the sum of flow times time distances. Those are two different objective functions, and the result or the resulting layout is going to be based on that type of objective function. So last time we covered the graph-based method. In this lecture, we're going to talk about CRAFT, the MCRAFT, and the MIP, which is mixed integer programming. So if you are familiar with operation research or linear programming, linear algebra, Those are the ideas that are behind this mixed integer programming process. So we're going to do a formulation of a problem in which we're going to have linear type of equations denoting the constraints, the objective function, and we're going to solve for that linear programming model. But we're going to begin with the CRAFT. CRAFT stands for Computerized Relative Allocation of Facility Technique. And this is an improvement algorithm, meaning that you are beginning with something. You're starting having an initial layout, and you're trying to improve that layout. Has a discrete representation, meaning that you can count the number of departments, and also you can count the distance. So it's a discrete type of representation. We use the from-to matrix. So we have information about the flow. It has a distance-based objective. So we are going to be looking at the distance multiplied by the cost associated with the flow. And it involves what we call a pairwise exchange, which means that you're going to be swapping the location of two departments at a time. So for example, if you want to know whether or not you get a better layout in terms of that objective function, that distance-based objective, by switching department 2 with department 3, then you can do that, and you're going to compute that objective function, and then you're going to compare it. So we'll see how this works. This was introduced in 1963 by Amour, Buffa, and Bowman. So these are faculty members. Remember the university, I think it was here in the States, but I don't remember exactly the campus. So they developed this. CRAFT is a tool used to help improve the existing layout of the facility, and the facility is improved by switching 2 or 3 departments to help arrange the facility in an optimal floor plan. So the considerations for this algorithm, they require, again, these 3. The from-to chart, which is, again, the chart that is telling you the amount of flow that is happening between departments. The cost matrix, so how expensive it is for you to move items from one department to the other. And then the distances, how far are you from one department to the other. So those are going to be determined for a given layout and an initial layout. So we're going to compute that for the initial layout. That's going to be our benchmark. And then we're going to start doing this swapping. And every time we change the configuration, we recompute the objective function, and we compare whether or not this is a good alternative. We do that for every possible acceptable swap, and then we choose the better one. So if we find one that has a cheaper cost, we choose that one, and then we recompute the centroids, and then we move to whether or not we do a next iteration. Depends on how good of a solution we have on hand. So I'm going to show you the steps in a minute. So what are the major features of CRAFT? It attempts to minimize the transportation cost. So transportation cost is computed using the flow, the distance, and the unit cost. So this refers back to this. Show you, right? So it's this objective function right here. They're minimizing the sum of the flows time distances. So it's the flow, the cost, and the distance. So that's the objective function: flow, distance, and cost. CRAFT is a path-oriented method. The final layout is dependent on the initial layout. So again, in CRAFT, you need to have something to begin with. This is not a construction algorithm. This is an improvement algorithm. So you start with an initial layout, and then you perform the iterations in order to see if you can improve that flow or transportation cost in this case. The assumptions that we make with this algorithm is that the move costs are independent of the equipment utilization. So it doesn't matter if you're using the conveyor 90% of the time or 50% of the time, the cost are independent, so those costs are not going to change. So for example, if you invested in a conveyor for departments 1 and 2, and now you're putting 4 there, cost of that conveyor is not changing. That's what this means. Move costs are linearly related to the length of the move. So we have that assumption, meaning that farther you have to travel, most likely is going to cost you more. So they are linearly related to the length of the move. And here are the steps. Okay, so we have 6 steps. We start with determining the department centroids. So we're going to have this block layout, initial layout, in which each block is representing a department. And we're going to find the centroid for each one of those departments. Then we are going to calculate the inter-department rectilinear distances. So for each combination, every possible combination of departments, we're going to compute the distance from centroid to centroid. Those are going to be rectilinear distances. So they're going to be following the path, the square configuration of the layout. Then using that information, we're going to compute the initial cost of the layout by multiplying the information in the front 2 matrix. So this is the flow with the cost matrix. So how much does it cost you to move this from point A to point B? And we're going to use that cost and we're going to multiply it by the amount. Craft then considers all possible 2-way or 3-way department exchanges and identify the best exchange from that iteration. So we look at every possible exchange, we find the best one, and then we assign to the best one the current layout. So that's going to be our current layout after completing an iteration. And then we use that current layout to perform an additional iteration. If we don't find a better configuration based on that new layout, then that means that that's the best option for us. But if we are able to find a better cost, let's say a cheaper cost for after the first iteration, then we continue the process until we find no better configuration for our system. So I'm going to show you that with an example. We update the layout and calculate the new department centroids. The above procedure is repeated until no further reduction in the cost can be obtained. Okay, so we continue doing this process until we find that, okay, after this iteration, if I do every possible swap, there's no better cost. So that means that I'm done. Okay, so let's look at an example. So I'm going to start with this layout. This is my initial layout. And the first step is to determine the department centroids. So for that, you have to find your origin. You have to decide where you're going to place the origin. And then based on that, you're going to be computing all these centroids. So for me, I'm going to be choosing this quarter as 0, 0. And then those centroid distances or coordinates are going to be based on that origin. So for, let me use another color. So for instance, for department 1, counting for X, this is 3. And for Y, this is also 3. Okay, so these are rectilinear distances. Yes, sir. No, we are going to assume that we're going to use positive distances. Yes, that's a good question. At the end, what we want to make sure is that we have the correct distance from the origin. Yes. For the origin, yes, in one of the corners. Yes. So as long as you're consistent, I mean, you can choose any corner of the layout. You just have to be consistent. So if you're choosing that corner to be the origin, that all your distances are going to be based on that assumption. As long as you're consistent, you choose one corner, you're consistent, you're using that corner for all possible distance measurement, then you're going to be okay. But you cannot do is change the origin for the either loop. Yes.
In real world application, or some other sort of external factor, or does it really even matter? You just need the measurements.
That's a good question, and the answer is it doesn't matter, because what you need is the distance, right? And as long as you're consistent, you choose the corner that you are is going to be easier for you to manage, and then as long as you continue using that corner, the distances are going to reflect that that's the origin. You should be able to get the same solution. Yeah. Okay, so we have the centroid for 1-1. For 2, go through the same process. So we have 3, 4, 5, 6, 7, 8, 9, 10, 13. And then 1, 2. For 3, 14, 15, this is 15, 16, 16 and a half. One, 2, 3, 4, 5, 6, 7, 8. Four, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 and a half. 1, 2. Five, we have 3. 1, 2, 3, 4, 5, 6, 7. For 6, we had 9.5. 7, 8, 9, 10, 11. Seven, we have 1.5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then for 8, we have the same for X. Sorry, 4.5 for X. And the same in terms of Y. So these are the centroids for every department. Yes. Yes, yes. It's not going to change, correct. So from here, we are going to find the distances between each department. Okay, so, but here's the trick. You don't want to go and do this for every possible combination, because if you look at the flow, this is the flow table. This is flow times cost. This is combining both the flow and the cost associated. Then you can just find the combination of departments that have an existing flow, right? Because if there's no flow between them, then you know it really doesn't matter. The cost associated with those two departments is going to be 0 because there's no flow needed between them. So if we are going to find the distances, we have 2 options. We can find the distances for every possible combination. Let's say 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, up to 8. 2, 3, 2, 4, 2, and so on. Or we can focus on those departments that have an existing flow. That will save you some time. It will make things easier too. So for example, if I look at 1 and 3, I know there's a flow associated with it. So I can look at the distance between those two. Those are rectilinear distances. So 1, 2, 3, 6, 7, 8. That's given here. This is the table that tells you this is a front-to chart. Okay, so this is telling you there's a flow between these two departments. Okay, so I know from 1 to 3 there's going to be flow, so I can look at that combination as part of my analysis. If there's no flow, then it doesn't matter. You can compute the distance, but at the end you're going to multiply by 0, so it's not going to make a difference in your analysis. So that's why I'm saying we should focus on those that have a flow, because those are the ones that are going to impact the design. Yes.
With that same thought, you also look at whatever one sets that have the highest amount of flow. Traffic want to necessarily start with them.
Well, you have to consider all of them. Not only the one that have, because for computing that objective function, you have to compute based on the overall, I mean, considering every combinations in which there flow. The objective function is looking at all possible combinations in which there exists a flow in the design. So going back into, so yes, you have to take into account all of them. Remember, you're going to multiply this by the distance. So you can have a high flow, shortest distance, that will have, let's say 20 times 1. The distance is 1, flow is 20. You say, okay, this has a high impact because it's very high flow. But when you multiply by the distance, it's just 20 units. Whereas you can have a flow of 2 and then a distance of 20. When you multiply, that's 40, and that can be added to your objective function. And that could be a higher impact into your decision. So that's why we have to take into account all of them. And we have to multiply by the distance. So now we are going into that part of the process in which we're finding the, let's see, the distance from centroid to centroid. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 1, 2, 3, 4, 5. So that's 18 and a half. So from 1 to 2, this is 0, right? So I know we can assume, well, let's not make 0. I want you to get confused. So an empty space in my front-to chart basically is representing 0 flow, right? So I'm going to be focusing on the ones that have a value. And you see, even though from 2 to 4, there's no flow, right? This is 0. But from 4 to 2, there's a flow. Okay, so going in one direction, there's no flow, but going in the opposite direction, there's flow. So next one will be this one. So between 1 and 7. So that will be 1, 1.5, 1, 2, 3, 4, 5, 6, 7. So that's 8.5. Next one, this one, between 2 and 8. So that's 1, 2, 3. There's 3.5. 1, 2, 3, 4, 5, 6, 7, 8. So that's 16.5. And you understand the process, right? So we go check which one. There's another flow here. So from 3 to 5, we go from here. Half, 2, 3, 4, 6, 7, 8, 10, 11, 12, 13 and a half, 14 and a half. And the rest of it, pointer, we have this one. So that would be from 4 to 7. 1/2, 1, 6, 7, 8, 9, 10, 11. And I'm gonna just complete the distance, but you see how the process is, right? You look at the combinations, you have to count based on the squares that are between those two centroids. So we have 11. We have another one here, that's 4.5. And then we have this one, 0.5, 6, 14.5. It's this one, and this one is 10. And then we have this one, 2. This is 8. Okay, so that's the distance table. So you start with looking at the centroids, finding the centroids. Now you compute the distances from those departments in which you have an existing flow. So you compute the distances and you tabulate that information into this distance matrix. So now that we have this, we can compute or calculate the initial cost of the layout by multiplying the front two matrix with the cost matrix. Okay, so we are going to basically use this formula, flow times distance times unit cost. And then we are going to compute the value for that associated cost for this initial layout. So we have the cost, distance, flow, and cost. So this one has flow and cost associated already together. So we just have to multiply this times this, 18.5, 20, plus this times this, 8.5 times 2, plus 16.5 times 1, plus 14.5 times 2, $11 times 2, 4.5 times 1, 8.5 times 1. $14.5 times 10. What else we have? 5 times 10. Plus 2 times 8. Okay, so this shouldn't be here. Apologize for that. I don't want you to get confused. So we have 8.5, 14.5, 10, and 8. Okay, so those are the right numbers. Let me make sure that I'm consistent, so you don't get confused later. So this should be 8 times 2. So 20 times 18.52 times 8.5 plus 1 times 16.5 plus 2 times 14.5, 1 times 8.5, 2 times 11, 4.5 times 1, 10 times 14, 5 times 10, yes. So this should be equal to 678.5. Anybody can double check that. Okay, so let me know if those numbers are not correct. Okay, so we have the initial cost of the layout. This is our benchmark. This is the initial layout. This is the information we have. We use that information to compute the current cost of the facility. Question is, we start swapping departments now, 2 ways to exchange departments. Can we find a better cost for our facility, a better configuration? So this is something very important. Let me highlight that. So only equal areas or adjacent departments are feasible exchanges. You can only do exchanges if you are sharing a wall, like here, 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 here. All those are sharing a wall, so you can exchange those. And if they're apart to each other, like 1 and 3, you cannot exchange those unless they have the same area. So 1 and 3 are not next to each other. 1 and 3, they don't have the same area, so you cannot swap them. If 3 were the same size of 1, even though they're apart, you can swap them. So only equal areas or adjacent departments are feasible exchanges. So we have the initial layout centroid table here. And then this is, I'll say, a little bit difficult to grasp, but this is how the algorithm is designed. So for example, if I do exchange 1 and 2, that will be exchanging these two departments. This one and this one. What the algorithm is going to do in order to avoid the recomputation of centroids for every step, what it's going to do is going to assign the centroids of 2, like you're seeing here, to 1. Okay, so basically what this is saying, we know that 1 is smaller than 2, but we are assuming that if we swap them, 1 is going to have the centroids of 2, 2 is going to have the centroids of 1. They're going to have the same centroid. The centroid is not going to change. Okay, so that's why you see here the original centroid for 2. Oops, I'm using same color. Apologize. So these are the centroids for 2. Since now we are exchanging 1 and 2, the centroids of 2 are now the centroids of 1, and the centroids of 1 are now the centroids of 2. So that's what swapping means for this algorithm. You're going to assign, so if you're going to exchange 1 and 2, the centroids that were originally assigned to 1 are going to be the centroid for 1 now is the centroid for 2. The centroid for 2 is now the centroid for 1. And you see, there's as an example of an invisible exchange, which I mentioned already. Exchange 1 and 3 is invisible because they are apart. They don't have the same area. Exchange of 1 and 4. See, 1, you can see now 1 has the centroids of 4, right? And 4 has the centroids of 1. So swapping means you're locating this new this department in the same centroid location of the department that was there. Okay, so, and we have to look at every possible combination. So for example, you see all those walls that I highlighted, those are possible exchanges. So you can do 1, 2, you can do 1, 5, you can do 1, 4. For 5, you can do 5, 7, 5, 8, 5, 4. For 3, you can do 3, 2, 3, 4, 3, 6. All those are possible exchanges. Okay, so you're going to come up with, and doing this by hand is tedious, right? Try to find one of you mentioned it, there's a computer base. There's used to be a adding for Excel to run the craft. With the newer version of Excel, that adding is no longer working, so I'm looking for a different alternative. But yeah, there's there's MATLAB code out there in other languages available for this algorithm. There's code for it. But for you as an engineer, you need to understand how this works, and that's why we're going through this process. So we got the exchange. These are two examples of feasible exchanges. This is an example of an infeasible exchange. So for craft exchanges, centroids first, then calculates a new table of distances. And then new layout costs and possible exchanges are evaluated. The one with the most savings is selected, and the centroid distances and actual layout are then updated. So that's the process. Now you got the new centroids for this exchange. You're going to compute the distance. Most of the distances are going to stay the same. only the distances of those departments that are associated with the ones in the exchange are going to change. So for example, if you swap 1 and 4, so for every department that is associated to 4 will updating the distance. Every department that is associated to 1 is going to require for you to update distances. So here's the exchange departments 1 and 4. This is the one that is going to give you the most savings. So for example, we look at going back here. Now, 1 has the centroid of 4, 4 has the centroid of 1. So that's the table we have here. So we exchange those centroids, and we also, based on that, we update the distances. So for those that were involved with 4 and 1, so this distance from 1 to 3 is now updated. So originally, from 1 to 3, we have 18.5. Now that we have swapped that department, right? 1 is going to be here. Now that we swap that department, 1 is going to be closer to 3. So the new distance will be 8. And same thing. So you have to look at now at the, have to go back here and assume that this guy is now 1, this guy is now 4, and recompute all the distances. These distances that we computed here. So going back here, we're basically saying this is 1, this is 4. So now we have to update these tables. And the result of updating that table is this one. Based on the new location of the departments, we update the distances. And after that, then we compute the cost. So we have to multiply the distances times the cost associated with the flow, the cost associated with those two departments. So I think we have that calculation here. So let's calculate the cost of the layout after changing the departments. Actually, it's not the case. So this cost will be computed as follows. And then remember that we have to compute the cost for, compute the distances and compute the cost for every possible exchange. So this is the exchange with the most savings. The cost is computed again based on the distance times the flow. So this will be equal to 8 times 20 plus 11.5. So this is 11 times 2. 14.5. We have this one, we have this one, we have this one is the same. So it's 16.5. Yeah, so this is showing you, once you get the distances, which are plotted here, are illustrated here, you multiply this times the function, cost times the flow, and you are gonna get the final result based on that multiplication. But the example here is showing you this is after computing the objective function for every possible exchange. We get the objective function. In here, I'm telling you this is the best solution. This is the one that gives you the most savings. So once you have identified that, then you have to go back and look at the actual layout and try to reconfigure your layout based on the actual information of the area, right? So we know 1 is smaller than 4, right? So we're going to be putting 1 in the location of 4, and that's going to create this weird shape for that department. But now, using that, we are going to find the actual centroids for the final layout, which is this one right here. And we go through the same process, right? For the rectangular ones, those are easy. You can find the centroids of those easily. The one that is going to create some challenge in order to find the centroid is this weird shape. So for those, if there's no way for you to arrange this, my advice is you have something like this might not be functional. So you might be able to somehow reshape other departments so this can look more as a square. And then it will be easier for you to compute the centroids. But if you have no other option, then you have to go back to your statics knowledge to find the centroids of areas. For the purpose of the exam, and in practical terms, instead of trying to find the centroid of this, it'll be easier for you to try to find a way to shape this properly. It's a square. But this example is showing you the actual centroid based on the shape, which is right here. And then using the centroids and the updated distances with the new centroids, we can compute the final cost of the layout, which is going to be cost distance times the flow times cost. So in this case, that's 20 times 7.5 plus 2 times 11.5 plus 1 times 16.5 plus 2 times 14.5 times 11.07 plus 2 times 8.43 plus 1 times 4.5 and times 4 times and that equals 355.79. This is the cost of the updated layout. The original layout cost was 678.5. So this is representing some savings. If we do ratio. This is original minus new divided by original. This would be about 47% improvement. So the final cost associated by just swapping 1 and 4 is giving you a reduction about 47%. Question now is whether or not this is the best. Okay, so after completing this step, we have completed one iteration. We have to repeat the process and see, okay, this is my new layout. Let me see if I can swap now based on this new configuration and see if I can obtain a better cost. So 3 iterations of the algorithm will take us to the final answer. You'll see that after doing exchange 5 and 7, and then exchange 5 and 8, the final cost goes to 345.29, which is not a huge difference when compared to the first one, but still give you some additional savings. So what I want you to do, okay, this is just craft, and this is why I do the review as well. I want you to go back and read through this example. So on Wednesday, I'm going to bring a new example. It's actually a complete process that I posted in the modules today. And we're going to go over that on Wednesday. So, yes.
I think we will have the practice, for example.
We are going to have a review on Wednesday. Yes, so on Wednesday, as part of the review, I'm going to go through an additional example of craft. Okay. Because I have other algorithms to show you. Those are not going to go in detail, but I need to show you those. But this one is the most relevant one, the craft for improvement. So again, the previous lecture, I showed you some construction-based algorithms. Those are based on, I mean, you started with nothing. And this one, these are improving based algorithms in which you start with something and you're trying to improve the layout. So for craft, the procedure adopted for using craft are determine the transportation cost of each departmental interchange, select and implement the departmental interchange that offers the greatest reduction in transportation costs, repeat the procedure for the new layout until no interchange is able to reduce transportation costs for your layout. These are the 3 major steps, which is what we did. So what are the pros of craft? You can evaluate many exchanges quickly, obviously under the assumption that you are coding the algorithm. Initial layout can be captured accurately, and craft allows for flexible department shapes, dummy departments. So if you want to block an area, you can do that. Fixed departments, if you don't want to move a specific department, you can also take that from your exchange. And non-rectangular buildings also allows you to evaluate non-rectangular buildings. The cons, sometimes you end up with some odd shapes, like the one we observed for the example. You have limited exchange options. If you are familiar with how algorithms work, you have coding experience, this type of exchange can lead you to a local optimal, meaning that you can get stuck in the search and might not be able to get from there to a better solution. So these are heuristics. They give you a very good solution sometimes, but not the best. Craft is path dependent. The starting layout makes the difference, right? So if you start with a good initial layout, your likelihood of finding a very good layout is high. If you start with a very bad layout, then it will change the process. Ncraft is a different, it's a, let's say a version 2 of Craft. This is similar to Craft, except that it can exchange two not adjacent departments, so it has that flexibility. Layout formation technique that allows easy shifting of departments. And the idea is that the facility is divided into bands. So if you have 3 rows of departments, then you can create three different bands. Layout form by starting at the upper left-hand corner of the building and sweeping the bands in a serpentine fashion. Two-way exchanges form until no further improvement is achieved. So this is a very, it's like an exhaustive search in which you're gonna be looking at possible swaps in these bands. So this is the idea. You're gonna have these bands, right? So one, you can divide this into 3. And then you're gonna be looking at possible exchanges within this flow. The way you compute the performance is the same as you did for Craft, right? So you're gonna be looking at the distance, the flow between departments. Limitations, it may be hard to fit the existing factory layout into bands. So if you don't have something like this in which you can easily show that you can split this into 3 bands, which is what this portion is doing. So 4 doesn't necessarily fit into a single band. So that will be challenging. Bandwidth assumed to be the same for all bands. And a fixed department may float when certain non-equal area departments are exchanged. So those are the limitations of this mCraft version of Craft. So again, you have the same type of information. You have the flow, you have the departments, you have the areas. mCraft asks for the length and width of the building and the number of bands. So you have to tell, okay, I have this size of a facility and I need to consider 3 bands. So it will compute the bands. And transform a layout by starting at the upper left-hand corner of the building and sweeping the bands in a serpentine fashion. It follows a particular sequence of department numbers, which we will refer as the layout vector of the field. So this is the sequence. Again, we have the 3 bands, and we are looking at the layout shown. The figure was obtained from the layout vector 1753248 which is supplied by the user as the initial layout. So what the algorithm is going to be doing is going to be swapping this vector, looking at possible combinations of the vector and then recomputing the performance of the layout. So mCraft performed 4 iterations, i.e. 4 two-way exchanges before terminating with the optimal layout. So you can see in the first iteration, again, this is computer-based, so I'm just illustrating you the process. Department 3 and 5 were swapped, these 2. Second iterations 3 and 8, these 2. And 4 iterations, department 2 and 3, these 2. Were swapped, and these are the costs associated with those swaps. And then this is the final layout based on those swaps for mCraft. So again, the idea for this one, it proceeds in the same way that Craft does, compute the performance measure the same way, but now we are constraining our swaps to be within these bands. Other methods and tools, mixed integer programming. Here we formulate the facility layout problem as a mixed integer programming problem by assuming that all departments are rectangular. So if you are an industrial engineer major, if you took operational research, i.e. 3340, we have a class that focuses on these type of models. You build these mathematical models, you formulate the decision variables, the constraints, and the objective function. But if you're a manufacturing manufacturing engineer major, don't worry. I mean, the idea is that you understand that you can formulate this as a mathematical programming model, in which you're gonna have an objective function that we have discussed already, the flow times the cost times the distance, and is the summation of all possible combinations. M are the number of departments. So for all possible combinations, we compute the summation of the flow times the cost times the distance. And we want to minimize this. Okay, so we formulate the objective function. And then we have some constraints. Again, you don't have to memorize this. This is a model that is available, meaning that it was formulated already for this problem. And what it does is it's going to have constraints that are going to impose the limitations of your layout. Okay, by looking at the, see here, we're looking at the distances computed with these centroid differences. And then based on the decision variables, we're gonna formulate, okay, so these departments have to be within this length, has to be within this width, the area has to be this much, and then some other constraints that are again based on the geometry of the departments and the area. So for those of you who are interested in operation research, this will be a good way to go. But if not, then we have these heuristics that we just discussed that are very good in terms of giving you a solution for your problem. This one, if you're able to solve this one, you'll get the optimal solution for your layout. It's not going to be like craft in which you're going to be stuck in a local solution. This one is guaranteed that if you solve it, you will get the best layout based on the conditions of your system. And that's it. So again, my recommendation for you is to go over this example for craft this today or tomorrow, and then on Wednesday I'm going to start with an example for craft, a complete example of craft, and then we're going to talk about the review. Any questions? Yes. That's a good question. Typically, I have a section that takes about 5 minutes in which I ask you about concepts, and those are multiple choice or true or false questions. And then I have a minimum of 3 problems, maximum of 4, like that in which you have to solve by hand. Obviously, I'm not going to ask you to complete the whole iteration of the craft algorithm, but I can design questions that will ask you, for example, can you compute the cost associated with this layout? Can you list all the possible exchanges for this layout? Yes, those type of questions I can ask and design a problem that will take you 15-20 minutes for that particular aspect of the lecture. So my design, I designed the exams for an hour, I will say. So I give you some 20-minute flexibility in which you can use to finalize the problem, but you have to you have to know the material. If you don't know the material, the exam, you're gonna run out of time. You have to be prepared. When you see the problem, you know what to do. It's not gonna be something that you have not seen before, but you need to know what to do. And that goes for online too. You sit down online and you don't know what you're doing, even though materials are not allowed, if you open the book or the lectures, you're not going to have time to complete the exam. You have to be, you have to know the material in order to do well. Yes. I'm going to decide tomorrow and I will let you know. I don't like that we don't have too much space here, being I mean, all of you come to the class. I don't know if they have enough seats. I think we have 31 students now. So I'm concerned about that. So I'm working with the office and see if we can do something about that. But I'll let you know on Wednesday. Okay? Any other questions? Good. So I'll see you Wednesday.